So my name is Gaurav Singh, the registration number 19BCE1835. This is the digital assignment one for the course CSE 1006, Blockchain and Cryptocurrency Technologies. And my topic for the day one is Byzantine fault tolerance. So coming to the introduction part. So since the onset of blockchain in 2008, which was introduced as a peer-to-peer electronic cash system, so many other cryptocurrencies were created at that time, each one with a particular mechanism of its own. So the one thing that nearly all cryptocurrencies have in common is the blockchain as the core element of their architecture, with a few exceptions, of course. So blockchains are initially designed to be decentralized, working as a digital ledger. So that is maintained by a distributed network of computer nodes. So for this reason, blockchain technology allowed creation of trustless economic systems. So where transparent and reliable financial transactions could be executed without need for middlemen. So nowadays, cryptocurrencies are being adopted as a viable alternative to traditional banking and payment systems. So which are heavily dependent on trust in nowadays. So just as in most of the distributed computing systems, so the participants of the cryptocurrency network need to regularly agree on the current state of the blockchain. And that is what we call a consensus agreement. So, however, reaching a consensus agreement on a distributed network in a safe and efficient way is far from being an easy task. So, how can a distributed network of computer nodes agree on a decision? So, if some of the nodes are likely to fail or be dishonest, so that is the fundamental question of the so-called Byzantine generals problem, which we will discuss in the next upcoming slides. So that gave birth to the concept of Byzantine fault tolerance. So BFT, uh, as in the Byzantine fault tolerance. So Byzantine fault tolerance is basically a computer system's ability to continue operating even if some of its node fail or act maliciously. So the term comes from a hypothetical called Byzantine generals problem. So the word Byzantine it's a Roman Empire, or also it's also referred as the Eastern Roman Empire or Byzantium. So this logical dilemma is about a group of Byzantine generals. So what is that? Each general has an army and a location surrounding a fortress. So there are many generals, and they must decide as a group to attack or to retreat. So if they all make the same decision, they are successful. But if there's a miscommunication or treachery, causing some generals to attack while the others retreat, so then the battle is lost, of course. So these type of problems are known as Byzantine faults, where all of them do not agree on the same point. So with any computer system with multiple nodes, so each node could be considered as a general. So the system's Byzantine tolerance refers to as whether it can keep working even if some of the nodes go down or intentionally try to deceive it. So to sum it up, BFT is the property of system that is able to resist the class of failures derived from the Byzantine generals problem. So this means that a BFT system is able to continue operating even if some of its nodes fail or act maliciously. So there is more than one possible solution to Byzantine generals problem, and therefore multiple ways of building a BFT system. So likewise, there are different approaches for a blockchain to achieve the Byzantine fault tolerance, and this leads to the so-called consensus algorithms. So now let us dive deep in the what exactly is a Byzantine generals problem. So let me explain it to you. So this problem was first acknowledged in 1982 as a logical decision puzzle. So it is based on how generals on the same side with different troops uh, have a communication problem in making decisions about the next move against the enemy. Since at that time there were no telephones, of course. So how would they communicate with each other if all of them are at different positions and they have to attack the same enemy? Uh, so as you can see in the diagram, which explains it clearly. So the problem states that like a group of generals with their army are about to attack their enemy. So they surround the enemy's castle with four different directions. So now how would they communicate the decision of attacking or retreating at the same time? Like it's not possible. So here a synchronized unconsensus attack on the enemy will be a success. So, but of course, there will be a problems that may arise during the sharing the decision from one channel to another. So some of them can be like, what if the messenger gets captured while delivering this decision? So what if an imposter altered the message that was supposed to be received? So how can a general make sure if he receive the message from the expected general? And what if that message is correct or not? And what if the other generals become traitors and they send their message to attack, but they actually retreat, causing other generals possible death? So how can a system be sure that each general will attack at the same time from their uh, location? So is there no way to trust each other completely? So blockchain seems to resolve this problem with a Byzantine fault tolerance consensus mechanism. So a solution to this dilemma can be, so what we want is the success of each general's team, right? So they need an algorithm that could adhere to the following conditions. So what if all troop generals need to agree on the next action plan that we want? So the generals should be trustworthy and loyal to the system. That is the first point. The generals must not get influenced to become the network traitors. So they need to follow the algorithm of the system. So the group of generals needs to reach a consensus or a decision, irrespective of the traitor's action. Like whatever the decision is, they should follow that. Or the system on the network should not lead to a 51% attack at any point, because that would end up uh, if there's a 51% attack at any point of time, it would favor each of the other side. Like it can favor like the majority of the favor could be on the traitor side or the victory side. So BFT is a consensus approach that resists a system to get into a Byzantine general's problem. So it also means that the system can stay intact even if one of the nodes or the general fail. So in addition, BFT aims to reduce the effect of malicious Byzantine nodes on the network. So as you can see in the diagram, there's a castle and there's the four generals. So these lines show what will be the message and the course of action. So now coming to the importance of BFT. So let's say from a computing perspective, BFT is important because it means what it means is that computer can function properly if certain components of the nodes are not working. So assuming that uses a computer system, such as, for example, an airplane. So that needs to able to work when not all of its nodes are at 100%. Like a airplane can work even if one of its engine fails, like the backup engines and the rest of the engines to make sure that the airplane is able to fly. So like we invest in cryptocurrency stocks or altcoins and everything other there. So that's another reason it's worth learning about this subject, the Byzantine fault tolerance. So what it is, it's a very crucial element of the blockchains that handle cryptocurrency transactions. So to understand it a bit in detail, so the details of BFT may sound like something that can only a computer scientist or a digital currency designer should worry about. To a certain extent, they are. So once a well-designed blockchain is implemented, the end user should not think about the Byzantine's faults because it's not their job to think about it. The developers have to make sure that it doesn't occur. So yet, since the blockchain technology in many places is still in design planning phases, so understanding BFT matters for people who want to apply blockchains as a novel solution in areas beyond digital currency. So what we know is that Bitcoin's approach for the Byzantine fault issue may not be practical for other blockchain applications. So what we can say is that BFT is a very crucial part of an effective blockchain, and there are multiple ways in which it can be implemented. So deciding on the which approach to take requires priorities of the community associated with the blockchain. There are many factors to be considered. So the solutions of the BFT that may have made system like blockchain possible may not work in blockchain applications in the future. Now coming to the practical BFT. So in an attempt to overcome the Byzantine problems, so there were two people, Barbara Liskov and Mikhail Kastrov. So they introduced the Byzantine fault tolerance consensus algorithm in 1999, commonly known as PBFT. So what they aim is to ensure a practical Byzantine state machine replication for tolerance, malicious or Byzantine nodes. So the PFT follows an asynchronous approach. So there are certain aspects of the PBFT algorithm which I'll tell you. So all the nodes are assembled in the sequence. So one network nodes serves as a leader node, and the rest of them are backup nodes. So the primary or the reader node serves the client's request. So it works as a moderator between the client and the backup nodes. Sorry, all the nodes are capable of communicating with each other nodes to check the honest nodes. So the honest nodes should be able to reach a consensus for the next global change in the network based on the majority role. So what it does, it identifies the source of the message to make sure it's sent by the correct sender. So ensures the message has not been modified or corrupted in between. So to sum it up, so PBFT is a system that has a primary node and secondary node. So these nodes should work together to reach a consensus, making the system one of the solutions for the Byzantine servers problem. So to say it in layman terms, so the client makes a request to the primary node. The primary node that sends the request to the secondary node. So the node that processes the request provides the service and respond to the client. So the client waits until it has received the same response from the, let's say, m+1 nodes, where m being the maximum number of false nodes, 40 nodes that the system allows. So in a practical BFT system, the maximum number of faulty or malicious nodes can't be equal or greater than 1/3 of the system total node. So coming to the BFT algorithm. So the algorithm highly depends on the condition that the maximum number of malicious or Byzantine nodes must not exceed 1/3 of the nodes in the network, as I said. So hence the security of the network uh, can be said is directly dependent on the number of total honest nodes. So in short, let's say a BFT can handle F40 or Byzantine nodes where there are 3F+1 total number of nodes on the network. So uh, now I'll tell you the process of PBFT consensus algorithm. So here's a diagram and I'll explain now. So a client sends a request to the leader node. Then the leader node floods the request to all the backup nodes, and all the nodes work on the request and they send a reply to the client. So the client waits for the F+1 replies from all the nodes with the same result. So F being the 40 number of nodes. So this PBFT mechanism has three phases. First being the prepare phase, the prepare phase, and the commit phase. So in the pre-prepare phase, the leader node sends out a pre-prepared message to each backup node. So in the prepare phase, after receiving the pre-prepared message, as a reply to all the other nodes, in the prepare phase. So what happens is after receiving that pre-prepared message from the leader, now it's the backup node's job to send the prepared message as a reply to all the nodes, including the leader. So a node is considered prepared only if it has received a prepared message by the leader and seen number of prepared messages from the other nodes. So in the commit phase, if the nodes are prepared, they send a commit message. If a node receives commit message, they can carry out the client's request. So the whole process of verification in a distributed system uses the concept of digital signatures. So the validity of a message and the sender are ensured using the sequence of number and metadata. So blockchain like Hyperledger, Fiber uses this practical Byzantine fault tolerance algorithm. So now coming to the pros and cons of the system. Uh, some benefits can be that the BFT doesn't require significant computing power or energy usage. So because there aren't any miners, solving complex equations for every block of transaction. So this makes it much more environment friendly than the proof of work. So the transactions don't need to require multiple confirmations. If the nodes are in agreement about a block of transaction, then it's confirmed immediately. So since all of the nodes can get in action, they all can share the rewards. So there isn't much variable between the nodes, earn reward as they can be in the proof of work or proof of stake. Now coming to some of the cons. So we can say that it's vulnerable to the Sybil attack. The Sybil attacks are named after a book about a woman with multiple personality disorder. So what happens is one party is able to get control of a large portion of nodes. So the more nodes there are, the harder it is to launch a Sybil attack. So it requires a lot of communication between nodes at every step of the process because it has to reach a consensus. So uh, this the time that's taken can be which can be a problem for a scalability standpoint. So the time taken uh, it's a bigger disadvantage of the algorithm. So now to conclude, so a blockchain may not have every node working at all the times. So there are obviously uh, some bad nodes that are trying to manipulate the transaction. Not bad nodes, but bad actors, you can say. So every cryptocurrency has a consensus algorithm, which is helped to achieve some degree of fault tolerance, Byzantine fault tolerance. So as a general rule, these algorithms allow the cryptocurrency to run normally as long as it said, through two-thirds of its nodes are functioning properly. So the Byzantine children's problem isn't it? It's a very interesting dilemma. So that eventually gives rise to the BFT systems, which are being extensively applied in various scenarios. So what now? So beyond the blockchain industry, a few cases of BFT system uh, are like they're used in aviation, space, nuclear power industries. So within the cryptocurrency context, so having efficient network communication along with a good consensus mechanism, it's vital for a blockchain ecosystem. So securing the system is an ongoing effort. So and the existing consensus algorithm are yet to overcome a few limitations, such as scalability. So nevertheless, the proof of work and the proof of stakes are very interesting approaches to the BFT systems, and the potential applications are certainly inspiring widespread innovations. Like there, people are just keen on making the systems better. These are some of the resources, and thank you. It's the end of 50.